So we're going to continue some U-substitution today in this video, and let's just jump in with another example. So number 5. So make sure you watch the first video on U-substitution if you haven't yet. All right. Excuse me. Let's take a look at the integral of tangent of x dx. So the first thing we would think about is this one of the functions that we learned at the beginning of the semester? Like, do we know a function whose derivative is tangent? No. So we don't have a short, quick antiderivative of tangent. So much like before, the first thing we're going to think about here is, because there's no inside function, it's not anything that yet looks like a U-sub. So we're going to go back to what we did before we had U-sub. If we had a trig function that we couldn't evaluate, what did we do? We tried to apply some sort of identity. So let's just go with our basic quotient identity. Tangent is equal to sine over cosine, sine x over cosine x dx. All right, so first thing, caution. This is not equal to, you can't just take the integral of sine divided by the integral of cosine. So there's certain times when students are much more tempted to do a mistake like that, and this is one of them. All right, so what do we have now? Now I have a situation, it looks a bit like number 4 in the sense that I don't see an obvious quote-unquote inside function, but what I do see is something that has a denominator. So I don't see anything raised to a power, I don't see anything inside of a trig function that's more than just an x. But what I do see is a denominator. So we are going to start off here. We are going to let our u equal that denominator. So u is going to be equal to cosine. And then our du, our differential, so the derivative of cosine is the opposite, or minus sine x dx. So this looks pretty darn good. So hopefully we're getting a little bit better at realizing once we get to that point, we're trying to match up anything that's left in the original integral that's functions of x's and dx's. And that's exactly what I have left here is a sine x dx. And down here, I have sine x dx. Awesome. So the only thing I really need to do is simply divide by this little negative, and so I have negative du equals our sine x dx. So hopefully we're getting more comfortable with this idea of isolating for anything that's left in the integral that's in terms of x. All right, so what do I now have? Looks like I have, in my denominator is my u, cosine of x was equal to u, and the whole sine x dx is really my negative du. Or if you prefer, you could think of that as 1 over u du. But you will see a lot of times where if there is not a anything in the numerator, where they do just kind of slide that du into the numerator. So as we look at kind of everything where it came from here, so there's my u, and then my negative du replace the sine x dx. All right, so now we're in business. We know how to take this integral. So this is negative natural log of the absolute value of u plus c. But then, of course, we have to replace, in our final step, we replace u with cosine of x. And so here is my final result. All right, so really what we did here, we can kind of do something definitely super similar for cotam. The way we would get the integral of secant and cosecant is a U-substitution. You kind of have to multiply in by a creative 1. I'm not going to go through all of those, but here's what I'm just going to say. I'm going to say similarly, one can show the rest of the trig integrals with U sub. And so what we're going to end up getting here, I'm going to make a little summary of all of our trig integrals. So we already knew a couple of them, right? So we already knew the integral of sine. So that was the opposite of cosine. And we already knew the integral, or the antiderivative of cosine, was equal to sine of x plus c. Now we've just shown tangents. Oops. Gosh darn it. I left off my dx's. Hold on. dx. dx. Okay. So we just showed this negative natural log absolute value of cosine x plus c. In a super similar way, you could do cotangent. I'm sure you could do that one on your own. Or as a matter of fact, in terms of tangent and cotangent, for the longest time for me, I did not have those two memorized. I would know they would be like some sort of natural log, and I would have to sometimes just kind of go through those again if I needed to kind of recall those. So this one comes in a similar way. Cotan is cosine over sine. You let u equal sine, and so on and so forth. Okay, now these last two, that's why I kind of said somewhat similarly, these last two kind of require, it's not quite as straightforward when you do these. They can be shown with U sub, and if anyone's super interested, shoot me an email or just Google, proof for the integral of secant of x, and you'll find a nice little video, I'm sure. I just don't want to take too terribly long with some of these videos here. But what you would end up with is natural log of the absolute value of secant x plus tangent x. You end up having to multiply by secant x plus tangent x as a version of 1 kind of over itself, and then you can do the U sub on that. And then the last one, integral of cosecant of x dx, is equal to the opposite or minus natural log of the absolute value of cosecant x plus cotangent of x. Okay, and again, that one you have to multiply that by that cosecant plus cotangent as a version of 1, and then it follows just with a U sub. All right, so these are now, we already knew the first two, so now you have the rest of them, in addition to some of those other special ones whose derivatives we knew from before. So you still have that special list, I guess I would call it, from earlier in the semester when you do those derivatives in reverse. But now we have all of our original 6 trig functions. We know their antiderivatives or their integrals. All right, so let's just keep continuing. Let's do one more example here, utilizing another trig example. So suppose I have the integral of, and this time I'm going to have 3 sine to the 4th of 2x times cosine of 2x dx. So this one's a little bit different. Probably the first thing I would encourage you to do, just like when you were learning derivatives, is make sure you realize that sine to the 4th of 2x is really sine of 2x quantity to the 4th power. Often rewriting it that way is helpful with derivatives as well as now with integrals. So initially you might kind of think to yourself, oh, we did one before where we had like cosine of theta squared, where something inside the trig function is more than just a plain old x or more than just a plain old theta. And that's true. That is often, if you look up here at this number 3, that is often going to be a choice for you. But down here on this one, yes, I certainly have these 2 x's on the inside. But what I want you to think about is, okay, pretend that wasn't there. So suppose that we did let u equal 2x, and then we'd have our du as 2dx, and we continued from there. What would I end up with in a best case scenario if the 2 x's weren't there and they were just plain old u's? I want you to think about how you would still have a product, a composition. So even with, and yeah, there'd be some constants here, and I'm not going to, you would still have a product and you'd still have a composition. So that is definitely an inside, but it's not what I would call the most dominant inside function. It's not the biggest problem we have. Now, some people do this and then they do a U-substitution within a U-substitution. So they do exactly what I have here. They get to this integral, and it's okay to do it this way. And they're like, oh no, I need another U-sub. And then they say, well, I better use a different variable. So now I'm going to let W equal sine U, and then kind of go from there. And that's okay. But my advice would be, let's start with what is like the biggest problem, I guess I'm going to say, or the biggest inside function. And really the biggest inside function that we have here is this whole sine of 2x function that's being raised to the fourth power. That is our biggest problem. That is our biggest inside function. So we are going to start by letting u equal sine of 2x. So we are going to start with that big primary inside function. Okay, now we're going to take our differential. So our du is going to be cosine, so the derivative of sine of 2x is cosine of 2x times the derivative of the inside, so times another 2 there, dx. And then when we look back at what we have, don't worry about the 3, don't worry about the 2. Again, if they happen to match perfectly, we'd be really glad, and it would make it that much easier. But the constant multiples in either location are never an issue. The issue is, of course, getting out any other remaining functions of x and the dx. So this is what remains as the problem, is the cosine of 2x dx. But a problem no more, because down here that is exactly what we have, a cosine of 2x dx. So we can very easily isolate for that by just dividing both sides by 2. So we have 1/2 du equals our cosine of 2x dx. And so there we have it. So we have our 1/2 du is equal to cosine of 2x dx. So let's see what we have here as we rewrite our integral. So I like to just kind of bring these constant multiples out in front. So the 3 just gets carried along. I like to put it out in front. And now I'm also going to have, when I do my green replacement, I'm going to replace the cosine of 2x dx with the 1/2 and the du. So again, it's all multiplication of factors, so I like to kind of put the constant multiple factor just out in front. So there's the replacement for the cosine of x dx. It is our 1/2 du. And now what we have is that sine of 2x, that got replaced with our u, and that u is just to the fourth power. So that's what replaced our u there. Oops, wrong color. Sorry. So try that again. So we have our u to the fourth. All right, so this looks promising because, of course, this is now something that we know how to take the antiderivative of, or we know how to integrate. And so what we really have here is our 3/2 as that constant multiple. Taking our antiderivative, integrating, we have u to the fifth over 5 plus that arbitrary constant. And then our last step here, we'll clean this up a little bit. And we will go back, maybe write that constant multiple as 3/10, and then replacing in the last step, replacing u with what it was originally, which was sine of 2x. And again, if you prefer, you could say the sine to the fifth of 2x, if you like that notation better. Otherwise, you did need those outer parentheses. Without that outer set of parentheses up above, it would look like just the 2x's being raised to the fifth. Now remember, and I'm not doing it all the time, somewhat just in the interest of time, I haven't done it yet today, but you can, always check these. So if you were to take this derivative of, bring down the 5, so we would have 15/10, or reduce the 5 with the 10, and you'd have the 3/2. And then it would be inside function, sine of 2x left alone, to the fourth power, times the derivative of the inside, derivative of sine, would be cosine of 2x, and then times the derivative of its inside, chain rule within a chain rule, will be times a 2. So those 2's would reduce, and I'm exactly left with the integrand that we began. So, again, that's always at your disposal. Some problems might lend themselves to that a little better than others, but that check is always at your disposal there. All right, so let's keep going. So we're seeing this isn't a short topic in the sense that lots of things come out of it. And so this section is just really, really important here. All right, so number 7, let's take a look at the integral of 1 over the square root of 9 minus x squared dx. Okay, well, it kind of looks like some of our opening examples, like, if I look at this, I kind of think, oh, well, there's an obvious inside, right? I have this u equal to 9 minus x squared, that's inside the function, and then du is negative 2x dx, but that's a big old problem, because at this point, if I was to try this, I would be at the point where I would have 1 over u to the 1/2, or if you prefer, u to the negative 1/2, and that's okay. But the dx, even if you isolated for it, even if you said, oh, well, I can get rid of the dx, can I? Can I just, divide by this, and then dx is du over 2x? Well, that would be like a negative 1/2, but here's the problem right here. It's this, the du is fine, but it would be this extra 1 over x right here that is a big, massive problem. So it's this, if we were to think about, so it's just as important for us at this point to recognize where the problems are. So if I replace my dx, if I was to replace that dx with this negative 1/2 1 over x du, if I was to do that, and again, maybe I start with what seemed good with my u there. This is the big problem. This right here makes no mathematical sense. Okay, we cannot integrate with respect to u if we have x's left in the integral. One of my colleagues always likes to say, I can hear her right now in my head. She tells her students there can't be any hanky-panky between the u's and the x's. So you can't have that. You can't just pull that out in front. We're trying to integrate with respect to u, and I got a function of x still in there. So this is going to happen the further you go in U-Substitution in this semester and next semester. You're going to try things, and you need to recognize when they don't work. This don't work. So we have to recognize that and be like, hey, that was a valiant effort, and it just didn't work out. And the more you do of these, the better your instinct is, and the more you'll kind of see these things happening in advance. So that just didn't work. So we just say, okay, so that was a failure. So this was our first try. So this was, our first try failed. Okay, so there's a little bit of an art to integration. And so first try failed, let's get after it again. So let's rewrite my original integral here. So 1 over the square root of 9 minus x squared dx. So my U-substitution didn't work, and that was my best hope. So I need to think about, and maybe it requires that we go back to like our list of some of these early antiderivatives that we knew. Oops, I did not mean to put that mark there. Erase that. So let's take a look at, what do I have here? Okay. So again, remember, we have 1 over the square root of 9 minus x squared. It kind of looks a little bit like this sine inverse. The integral of 1 over the square root of 1 minus x squared is sine inverse. Maybe we can make a go of that. So let's go back here and see what we can think about in terms of that. So what we want to kind of think about here, so my big thought bubble off to the side. So here's something that we know. So we know, what do we know? We know that the integral of 1 over the square root of 1 minus x squared dx, we know that that is our sine inverse of x plus c. All right, so what about this doesn't match up perfectly? Well, so what's my problem here? And my problem here is the 1. So this is the part that right now is, let's just call it, it's the, well, maybe that's not the problem. What's the problem in the integral? The problem is in the integral, right? So this is the part that doesn't match. Okay, so this is my problem then, with it not yet matching. All right, well, how could I get a 1 there? So let's think about doing a little bit of just some algebra on this. So let's take, and this may seem a little strange, but let's factor out that 9. So if I factor out a 9 times the quantity of 1, but then if I factor out a 9 from the second term where there wasn't a 9 to begin with, I'm going to have to put a little 1/9 there, so it would remain mathematically equivalent. So if I now distribute, let's just check, 9, yep, minus x squared. So those two are equivalent. So the nice thing here is that with multiplication and square roots, you can actually, what I like to say is split the radical. The square root of a product is the product of the square roots, to say it a little bit more formally. But you can split a radical if you have multiplication or division, not with adding or subtracting, by the way. All right, so now I'm getting somewhere. Obviously, this square root of 9 is just going to be a 3 here. So I have the 1 that I need now, so that's good. Okay, so I like that. So I'll put a little smiley face here. That's what I wanted. But what's the problem now? So now I have a new problem, and my new problem is this 1/9 there. So here's my new problem. But this is really the inside. This is in a location that's the inside of this original antiderivative function that we know. So I can think about this location here as really being the inside of this particular antiderivative function that we know. So that means because this problem corresponds to the inside, like where the variable portion is of that original integral, then I can do a U-sub. So we're going to deal with this problem. We're going to be able to deal with this one with a U-sub. But before we do that, let's do just one more kind of rewrite on this. So first of all, let's just bring this 1/3 maybe out in front of our integral, just for right now. And then I have 1 over my square root of 1 minus. And what I'm trying to do is I'm trying to think about if that x that I have kind of highlighted up there, if that is my inside of this function, right? That's what I'm saying to you, is that that's the inside portion. If that's the inside, I gotta figure out what goes inside that's being squared. So I have to figure out what this right here, what this inside is. Okay, so what squared is giving me 1/9 x squared? Oh, okay, well those aren't too bad. Those are perfect squares. So that's a 1/3 x. So 1/3 is squared as the 1/9, and then of course the x that gets squared. Okay, so now I kind of see here what my inside function is going to be. So this, if it's anything more than just a plain old x, can be dealt with a U-substitution. All right, so let's give this a go. So what do we now have? So we're going to have our, we just identified here that our u, our u is going to equal this 1/3 x. So my u is going to equal 1/3 x. So there's my u. All right, so that means that my du is just going to be the 1/3 dx. Oh, hey, that's kind of cool. That 1/3 that I had pulled all the way out in front, we're kind of back to a situation where it's kind of one of those nice, perfect situations that emerges when you get the right constant multiple. So I'm going to just slide it right back on the inside just for visual purposes. Mathematically, it's the same. But now I'm going to recognize that my 1/3 dx, perfect, that's du. So we like it when that happens. So let's see where we're at now with our integral. So we're going to have our integral is going to be our 1 over the square root of 1 minus u squared. So our u here was just replaced. That was originally the 1/3 x. And then the 1/3 dx, that whole thing is equivalent to our du. So that's my du. And finally, we have something in a form that we can directly state this is equal to sine inverse of u, or arcsine if you prefer, plus c. And then our last step, of course, is to go back and replace that u with what it was equal to, which was 1/3 x plus c. Or you could write it as x over 3, whichever you prefer. Okay, so what I want you to observe here, and you can always go about these problems this way. So first of all, if you see something that has this binomial, plus or minus, like a squared minus x squared or x squared plus a squared, sometimes under a radical, sometimes not, go back, take a look at your list of the integrals that result in those inverse trig functions. Maybe you're lucky and you have a perfect match. Most of the time you're not going to. So the first thing, if you're going to do this process that we just did here, the first thing you have to address was this first problem that I set up here was the 9. You need that to be a 1. If it's already a 1, great. If not, factor it out. Once you get that 1 here, whatever is inside of that second term, in this case it's the second term squared, the square term, that's your inside function. So then you do a U-substitution, that's the inside, in order to get just a u squared. This will always work. And a lot of your instructors in Calc 2 may always kind of go through it in this sort of full process here, and that's great. But what I want you to think about here is there was really nothing special about 9. So I want you to observe that this location of 9, that 9 that was right here, let me erase this in a minute, but that 9 that was up there, so that 9 is equal to 3 squared. So if every place I had started off with a 9, if I just went through and put an extra tail on my 9, and I thought of it as an a, let's say, and called it, well, not the 9 itself, sorry, but if I thought of it as an a squared, right? So this 9 happens to be a perfect square. So if this number that's right there happens to be a perfect square, so if I, instead of having, erase that big blob, if I went through this whole thing and instead of writing 9, if every place where I had a 9, I just said, oh, that's just some number squared. That's just an a squared. It happens to be 3 squared here, so it happens to be the 3 that's squared. But if I just said, oh, it's just an a squared, guess what? All the way through this whole thing, that a, which was the 3, that would have just been an a in that denominator. So in some ways, and there are instructors that will also refer to what I'm going to write out here as kind of a shortcut for some of these problems. So I'll say similarly and in general. And some books don't even write this out, some do. Some instructors don't refer to these, some do. I sort of feel like my job is to give you both. So similarly, and I'll just say and in general. So similarly and in general. What we would get, so let's rewrite this first one. So what I'm saying is what we just did, there was nothing that was unique about the 9. It was some number squared. And incidentally, even if it was 5, you could think of it as root 5 squared. It'd be kind of awkward, but it's still, any constant can be written as its square root quantity squared. So there was nothing special about the 3 squared that was there. There was nothing special about that 3 squared. If I went through and did exactly what we just did up above, we would simply end up with the same result, and it would be sine inverse of x over, instead of 3, it just would have been x over a. So if you have something of the form 1 over the square root of a number minus x squared, you could use this, what I'll call shortcut formula. Now, other ones can be the other, I'll say equivalent types of problems can be shown in a similar way. So if you have 1 over a squared plus x squared. Now if it's just 1 over 1 plus x squared, that's one of our quick straightaway, that's the arctan of x. But if there's an a squared, we would go through a similar process as what we did up above. And this time, when you would be done, you would end up with 1 over a of tan inverse of x over a plus c. And lastly, if you had the integral of a 1 over x square root of x squared minus a squared dx. This would come out to be 1 over a secant inverse or arcsecant of x over a plus c. Now, if anyone happens to be watching this video that's not working out of our Sullivan book, double check with your book. A lot of times they would have an absolute value around that x. Sullivan defined the inverse trig functions a little bit differently on a different restricted domain to start, and that sort of avoided some of those issues. So might be a little different in your book, just so you're aware. If you're somebody who's not using the Sullivan calculus book, then yours might look a little different there. Okay, so these are now kind of 3 other ones that we can refer to, but again, it would have to match up exactly with these forms. The thing to be careful of on all of these is that the inside of these functions is where the x is. Okay, so if and when, not just if, when, I'm going to even say that. So it's not like, oh, that may not happen. It will happen. Okay, so when it's of this, maybe one of these structures. So when it's of one of these setups or structures, this is getting verbose. I'm going to stop my writing with just saying the inside is where the x is. And let me just verbally say then, if that, in that location, if you have more than just a plain old x there, you're going to need a U-substitution. Okay, so the inside is where the x is, and that x needs to just be a plain old x in order to kind of use one of these formulas directly. If it's not one of these formulas exactly, then it needs a U-substitution where you see that x. kind of like we did in the above example, but even when you have something like this, you're still going to need to know how to do U-substitution. So how can I say this in a concise way? So you'll need to use a U-sub if it's not just X. I guess that's the best way to say it. So if it's not just X in those locations, you are going to need a U-sub. Okay, so that's still, even with these shortcut formulas, that's what you have to watch for. And that's why some teachers who don't like to give these formulas, they'd like their students to just be in the habit of recognizing that in every single problem. So they don't kind of fall into a trap of forgetting that they need a U-sub when they don't have just that X squared in those locations. All right, so we're going to stop there. This has been plenty long, and when we come back next time, we'll maybe do another example or so, and then we will kind of also work in U-substitution with some definite integrals as well next time.